This is going to be the third in this series where I'm actually looking at one of my old textbooks, Modern Calculus with Analytical Geometry, Volume 1, A.W. Goodman. And I'm on Chapter 1, page 7, looking at Problem 4 of the exercises there. Underneath proof, the proof is completed. Actually looking at having gone through, looking at superscripts and subscripts again, inequalities and identities. And this is actually an inequality identity. It's reflecting on that section that I looked at. How do you know whether something's an equality or an identity? And obviously, and of course you probably wouldn't know this offhand, but if it's equal all the time, which is what I'm looking for, if it's true all the time, then that's an identity. But if it's only true some of the time, it's a conditional equation based on particular conditions. The idea of calculus, and we call it modern calculus, but it started about 300 years ago, and perfection came about 100 years ago. So it's been around a while. It's not part of our common vocabulary, other than I think it strikes terror in a lot of people's hearts. But I'm using Excel and going through and setting up tables by opening it up, going to insert at the top, clicking on scatter, and let's see, and then selecting the table of choice. And I did not the straight lines. I did the points, which each one of these would be a point with smooth lines connecting them. And so that's what you're going to see appear on this page. And I selected data points. I think I went down through 12 on my list, but I probably won't use it for most of the program because I think it makes a prettier picture to go a little bit at a time. So I'm looking at sin x squared, and it's kind of a weird way to write it, use it, but makes sense, plus 2 times cosine x squared equals 1. And of course I have the first point laid out here where where the x is equal to 0. This 0 means that that sin x squared, when x is 0, it's equal 0. And also where 2 cosine x squared is equal to 0, 2 cosine x squared is equal to 2. And when you add 0 plus 2 together, it equals 2. Pretty straightforward when you're dealing with rounded real numbers like that. But I built this table based on pi, which describes a wave as well as a circle, because the definition of pi, well, actually pi is a Greek letter, the 16th of the Greek letter, but the way we use it in trigonometry as well as calculus is to identify a kind of number is that? Irrational number. Yeah, that's right. It's a ratio between the circumference over the diameter of a circle. Okay? So circumference is the distance around the outside, and diameter a line through the middle from one side of the circle to the other, straight through. And that's the diameter. So you take those two numbers, whatever the measurement is, and put them over top of each other, and you come up with this non-stopping digital number that starts off 3.141593. So that's what I'm doing. And if you're a track star, I'll try to think that way. I did run track a little bit at one time. But so the quarter way around for sin x squared is from 0 to 1. The next quarter will get us halfway around, which returns us back to 0. And then the next quarter turnaround, it gets us to the third quarter around, and it's back to 1 again. So we went from 0 and the points in between not being, they're being between 0 and 1 and then 1. So this equals what my equation says it should be, 1. But all these other points don't. Okay? But I haven't looked at this portion of the equation. It could be that when this is up, this is down, and vice versa. So it could equal 1 all the time. I just don't know yet. But let's go ahead and show the rest of the sin x squared. And you see what this is what it looks like between 0 and 1. And I think this represents 3 loops. Yes, it does. Okay. So we did in the last one. Now let's look at the next one. Go through the plus sign and come to 2 cosine x squared. So we know the first point is 2, and so it drops to here. So this is 0, this is pi over 2, and that's the number showed up in the little box, 1.570796327. Right. Let's go halfway around. Our pi, so it comes back up to 2, and it does cross 1 a couple of times. So at this point, somewhere in the middle between this point and that point, that has to be point 2, and this is point 3. Is that right? Yep. It's kind of halfway between those points. So if I wanted to find it for sure, I would decrease this increment, see if I can find that point, or solve it using this equation. But let's go ahead and map it all for that, and you can see how it lines up. So to make a long story short here, what I'm going to do is solve for y and see if y is equal to 1 all the time, and even with the first one is not equal to 1, but let's see if it shows up to be 1 anytime. And I could pretty much guess it does, but it might just throw the combining off the charts. Let's do the first quarter turn. Now notice what happened. As this one drops, when it gets to 0, and this one goes to 1, 0 plus 1 is equal to 1, which it says here. And this is 7.5 e exponential, I think it's minus 33, and that's a power, if you will. And so that's a very small, close to 0 number. That's why it's showing up really on the close on the line. So I'll give that a pass. Let me get rid of the rest of these numbers until I need them, because they cluttered my little drawing here. Okay, so you see this is where it goes. This is what's going on. There we go. Now let's go a little bit more around, halfway around, if you will. This is pi around. So halfway around, it's making this design, and it looks like, based on the way the red is cosine as it dips down and loops up, and the sin squared one is the blue. It looks like the junction, or the additive, the plus sign between this equation is a mirror image, looks like, of the sine, if you will. That's pretty, hey, it's interesting. Let's see if I can make it repeat itself. Let's do another full loop. Does. This represents beginning, halfway. Beginning again, or the end of the last one. Halfway. The beginning or the end of the next one. So let's make a next one. So this is pi equal 12.566. If you're a track star, you can kind of figure out what that might look like if you're circling the track time and time again. And as you're probably doing your math as you're running, you're like, oh, I'm doing a sine cosine sine squared 2x 2 cosine x squared and you probably will lose pace. I used to like to run like that, though. That was always fun, putting my mind on something else as I was doing the chores of the field duties. Here we go. This is good. I like the pattern. This is reflective. It's definitely telling me, and this is one right here. This vertical axis is what I was looking to see if these two combined together was one all the time. And I can tell you it's only one part of the time, which means this is a conditional equation. The vote is conditional. There it is. Talk to you later.